My name is Sergio Gonzalez. I'm AI research engineer in Inventor Corporation, and I'm going to present the work Interpretable Estimation of the Risk of Heart Failure Hospitalization from a 30-second electrocardiogram. This is the outline of the presentation. I will first give an introduction of the project, then give a bit of background related to survival analysis, and then go into the framework that we have designed for this problem or this application and give some conclusion. So the project overview. This comes from a hospital, Chang-Hung Memorial Hospital in Taipei, that entrusts us with a data study related to cardiovascular disease. The objective of the project was to estimate or predict the development of some cardiovascular disease using AI models and providing some interpretation for them. This data involved 21,000 subjects that were monitored for a maximum of 11 years and minimum of 2 years for cardiovascular disease. We include data, or the data set have some clinical data related to the age and sex and comorbidities of the subjects. Also, we have some Holter ECG recording of 24 hours, several record per patients, and we have some laboratory data. Given this data set, we went directly to use survival analysis because it's a field that allows us to learn from time to event data and are able for us to estimate the risk of having the disease. Also, we can maybe estimate the probability of having the disease and even the time. Also, they are capable to leverage sensor data. Sensor data are those cases, those patients that we haven't observed the event during the study. And that doesn't mean that patients are healthy, it's just that we haven't observed that event. They could be ill and then after, for example, in this case, after the fourth year, then develop the disease. But we didn't observe that because we finished the study at 2020. For survival analysis, one of the most common model is Cox model because it's easy to interpret, but it's also a very simple model. We have a very strong assumption. Then machine learning and deep learning methods have been recently adapted with great success, but are more difficult to interpret. This is the next. I'm going to speak about the framework that we have designed. They have three different or distinctive parts: data preprocessing, modeling, and model interpretation. So let's go first for the data set that we used. For features, we use clinical data and ECG recording, the first recording that we have for per patient, and we use a 30-second strip. We did this because we want this to be a fast and economic test to check the probability of having CHF. CHF is congestive heart failure. That is a condition where the heart muscle doesn't pump blood well anymore to the body. And for labels, we have the observation. That is, if the patient have been hospitalized for CHF during the study, with CHF during the study, and duration, that is the time to CHF, or the amount of time that we have been observing the patient. Related to the ECG, we needed to extract some features that were reduced that help us to later on to interpret the models. And then for that, we extract some heart rate variability features and some shape features that we call that are related to the PQRST complex that are the main way for the ECG. For doing this, we first segmented the data in 30-second segments. Then we filter normalize the ECG and then perform the R-peak extraction, for which we can extract the HRP features. And then after that, we have extracted each of the cardiac cycle of the 30-second segments, resample the cardiac cycle, and then compute a template by averaging each of the cycle together. And from there, we can extract the different wave from the ECG, as we can see here. Next, I'm going to speak about the model. For the model, we use string gradient boosting, which is a gradient boosting ensemble that builds decision trees on the model residual in each iteration. And specifically, we use the AFT variant that extends the accelerated failure time model, so it's a survival analysis model. And this survival analysis assumes that our distribution or our target domain, which is the time to the disease, is equal to our prediction model plus a given random distribution that is defined as a parameter of our model. And by using this expression, they allow to build a model that is optimized by maximizing the likelihood. And what this means is for uncensored data, those people that we have observed the time to event. So we'll try to maximize the majority of the probability of that on that time, the one we have observed. While for sensor data, the one we haven't observed, we will have the probability will optimize it or look for the majority of the probability in the in an interval, which is the ending of the observation and the future. Here, I present some performance comparison where we compare the XGBoost model with other two survival analysis model, DeepHeat, that is based on a neural network, and the Cox model that I mentioned before. And we can see that XGBoost model outperform these two other models in the majority of, well, in all the metrics that we use that are related to survival analysis. Plus, we have done an additional study where we try to extend the amount of minutes that we use in the ECG segment. That is, we try to enlarge the ECG, even using the whole 24-hour recording. And we can see that, yes, the performance of the model improved using more data, but this improvement is not very high compared to the original results, especially for XGBoost, which probably is not necessary to record that much data to have more or less good result. And the last step is the interpretation. For interpretation, we use Shap values. That is a model agnostic interpretation framework based on Shapley values that come from game theory. And Shap values provide us an explanation given some feature values x as an additive contribution on our model expectation. What that means is if we have the mean or the average of our predictions plus the contribution of the Shap values for each of the feature value of a given x, meaning a given feature vector, is equal to the prediction of our model. And this is true for every single sample of test in our prediction. So this one will help us to interpret the model in two ways. We can give a global interpretation and a local interpretation. The global interpretation allows us to understand generally the model behavior for each of the features. So we can represent how the feature value will change the output of our model. And here I present an example for T amplitude, where we can see that very low values of T amplitude represent a higher risk for having CHF. These lower values of T amplitude correspond to invert T wave, while normal, more or less normal standard elevated T correspond to lower risk of having CHF, as we can see here. And then later on, as when we have like a very elevated T amplitude or T wave, we can see that the model output decrease a bit, even some point lead to a higher risk of having a CHF. Also, we can interpret the model locally. And briefly, I can say we can give the predictions. We can also observe from where we took our features, and then we can give the prediction in terms of probabilities on each of the contribution of our features. For conclusion, we have shown that it is possible to estimate the hospitalization of CHF using 30-second ECG. For us, interpretation was a key component, and for that we needed to extract some reduced set of features and to use explainable AI with SHapley values. For this project, also we have a margin for improvement because we can reiterate on the feature extraction to try to reduce error or extract other usable features. But not only that, we can use more complex models that learn directly from signal. However, the interpretation will be more difficult.